Okay, so that r and theta that I've been referring to so far, those of course have technical names. So I said that if you have a complex number, r is the distance from the origin, theta is the angle measured from the positive real axis, okay? So that r that we've been talking about, that's called the modulus of your complex number. And the way you write it like this. You use the absolute value symbols. So if you have a complex number, that symbol doesn't mean absolute value anymore, because absolute value is reserved for purely real numbers. So if you see that symbol around a complex number, it's referring to the modulus of that complex number. And here I've written that the modulus of x plus iy is the square root of x squared plus y squared. So that's just the definition. So again, it's easy to see why that's true. So if you've got a complex number here, x plus iy, if you draw like a right angle triangle, so this is r, well this is x, this is y. So by Pythagoras' theorem, right, r squared is going to be x squared plus y squared. So that's all that is. Now an important result to know, which I think you'll use quite a bit, is this one here. That when you take a complex number and you multiply it by its conjugate, you actually get the modulus squared. And it's easy to see why this is true. So let me just quickly show it to you. Okay. So if I let z to be a random complex number, so let's say z is x plus iy, okay, then if I do z times z conjugate, I get x plus iy times x minus iy, which is a difference of two squares. So therefore I get minus I squared y squared. And remember, I squared is negative 1, so this just becomes x squared plus y squared. But remember from before, the x squared plus y squared is the same as saying the modulus of x plus iy squared. Or in other words, the modulus of z squared. So it's easy to see why that's true, but this is a result we use a lot, and I think I'll use it a fair bit in today's examples. So that's something to definitely make a note of. Okay, so that's about the modulus. Now the angle theta that we've been talking about so far, that's called the argument of z, and we write it like this. So we use a symbol, just the letters ARG. So ARG stands for argument. Now notice that the argument of z, the way we've defined it as just being the angle measured from the positive real axis, right? That argument is not unique. And the reason for that is that you know that if you have any angle, if you go around one revolution, so if you go around by 2 pi, if you add 2 pi to that angle, you come back to the same location. So every time you go around in a revolution, or multiple revolutions, whether it be clockwise or anti-clockwise, you land in the same position. And so those, you can have the same complex number, and you can write its argument in infinite different ways. So for example, going back to the problem we had on the previous page, right, we had that complex number, and it was somewhere over here. And when we did it, we found that the argument was 5 pi on 6, right? But again, if I go around in one revolution, so if I add 2 pi, which gives me 17 pi on 6, right? I get the same complex number. So it would be perfectly valid to say that the argument of that complex number, z, is 17 pi on 6. Or I could add another 2 pi, or I could subtract multiples of 2 pi. And that will give me the argument for the same complex number. So that's why we're saying the argument of a complex number is not unique. So to get around this, what we have this notion of the principal argument. And notice with the principal argument, it's written slightly differently. It's a bit subtle. The only difference is instead of using a lowercase a, we use a capital A. So when they use a capital A, right, they're not referring to the argument, they're referring to the principal argument. So the principal argument means the value of the angle, like we said, but when you take the range to be from minus pi to pi. So for example, in the case of the complex number we had before, the principal argument would be 5 pi on 6, because 5 pi on 6 lies on that range from negative pi to pi. But it would be incorrect, for example, to say that the principal argument is 17 pi on 6, because 17 pi on 6 lies outside this range. So the principal argument is just the angle, the value of the angle that lies on that interval from negative pi to pi. And in fact, some people, when they refer to polar form, they require that the argument be the principal argument. So you have to consult your lecturer about what their preference is, but some people make that requirement. So if they say take a complex number and put it into polar form, then they require you to give the principal argument. But I think, generally speaking, the convention is it doesn't really matter. Whatever argument you give is fine. Okay, so let's do some examples regarding modulus and argument, just to get comfortable with these ideas. So, first one that we'll look at is this one here. So this example is actually a result. It's a result that it's kind of a tool that you use in harder problems. But I thought I'd take this opportunity to show you how to do it, and hopefully that'll help you to remember it as well, because I reckon you'll use this trick quite a bit in your studies. So basically what we want to show that if you have a complex number and its modulus is 1, then the conjugate is the same as taking that complex number to the power of minus 1. So let's have a look and see how we do it. So, okay. We know any complex number can be written in polar form. So r cos theta plus I sine theta. And remember, this r was the modulus. Okay, so if we take the modulus of z as being 1, that means z has this form. Cos theta plus I sine theta. Right? In that case, z to the power of minus 1, well, you know z to the power of minus 1, of course, that just means 1 on z, which is 1 over cos theta plus I sine theta. Now remember the trick we spoke about before. In order to get out of this pickle, right, you take the conjugate of the denominator, which would be cos theta minus I sine theta, and you put that on the top and the bottom. And so now this fraction is essentially 1, so I'm just multiplying by 1, so I'm not doing anything which is invalid. But what I get, on the top I get cos theta minus I sine theta, and again on the denominator I have a difference of 2 squares. So it's going to come out to be cos squared theta minus I squared sine squared theta. But again, keep in mind that I squared is equal to minus 1. So this becomes cos theta minus I sine theta over cos squared theta plus sine squared theta. And we all know that cos squared theta plus sine squared theta is 1, right? Very famous identity. So that denominator equals 1. So this comes out to be cos theta minus I sine theta, which if you think about it, is just the conjugate of z. So in other words, I've shown that if the modulus of z is equal to 1, then the conjugate of z is the same as saying z to the power of minus 1. So like I said, this is quite a useful result. I would say it helps to keep this one in mind when you're doing trickier complex number questions, especially if you're working on the unit circle. Because when we say the modulus of z is equal to 1, right, it means that the distance of z from the origin is equal to 1. So it means that z lies on the unit circle. So if you're doing a question where you're working on the unit circle, helps to keep this in mind. Okay, There's another important result or idea that we use a lot as well, and I thought I'd show you this as well as an example. So we want to show that if you have two complex numbers, z and w, then the distance between them is given by the modulus of z minus w. So usually we just tell students this, right? We just tell them to remember this, that if you want the distance between z and w, you just find the modulus of z minus w. And this is of course something that you do need to remember. It's a very useful fact, but I think it will be quite beneficial to see why it's true as well. It'll help you to get comfy with the ideas of modulus a little bit more. So let's have a look how this goes. So I'm going to draw my argand diagram again. So I got two complex numbers, z, w, two random complex numbers. So let's say z, for instance, is a plus bi, and w is c plus di. Right? What I want to do, I want to find the distance between them. So I want to find d, where d is the distance between them. Now if you think about it, you can think of d as being the distance from AB, thinking of this as a point on the xy plane, to CD. You can think of it in that way, because really the point Z corresponds to the point AB, and the complex number W corresponds to the point CD. And now if you use your distance formula, this just comes out to be the square root of C minus A squared plus D minus B squared. Right? Now, let's show that this is the same as saying the modulus of z minus w. Well, if I figure out the modulus of z minus w, then this becomes the modulus of a plus bi minus c plus di. And so I get a minus c, take out the I, b minus d. Now recall that we said the definition of modulus, we said modulus of x plus iy is square root of x squared plus y squared. So using that idea, you get square root of a minus c squared plus b minus d squared. And this is obviously the same as saying the square root of c minus a squared plus d minus b squared. Because we're squaring, it doesn't matter if we multiply the inner bracket by minus 1. And now you can see that this is the same as this. Or in other words, d, the distance between z and w, is the same as saying the modulus of z minus w. So that's why that's true. And like I said, this is a very useful thing to remember. I'll also show you why this is true. Maybe I'll give you a bit of a more visual argument as to why this is true. So let me draw the complex plane again. Okay, so we got this complex number z, right? Oh, whoops, let me just fix this. Okay, so we have this complex number z. So let's say it's up here. And we also have a complex number w. So let's say w is here. Okay. And think about what it means to do z. Oh, sorry about that. Think about what it means to do. Think about what it means to do z minus w, right? This is the same as saying z plus negative of w. Now, negative of w So if you take the negative of w, then you're taking the real part and you're multiplying it by -1, and you're taking the imaginary part and you're multiplying it by -1. So basically it will be, oh, that was a pretty bad drawing. It will be, one second. So it will be here, right? Negative w will be here. And now if I add z with negative w, remember what I said before, adding complex numbers, it just works like vector addition. So it'll be somewhere here, right? So this point corresponds to z minus w. Now the modulus of z minus w, right? That's the distance of z minus w from the origin. So this distance here, right? This distance is z minus w. Now if you think about it, that distance is the same as this distance. Because the way I've added these complex numbers, I've really formed a parallelogram. It might not show in my drawing because my drawing skills are terrible, but this right here is a parallelogram. And so this side here, which before I called D, has the same length as this side here, which I just established is the modulus of z minus w. So this is a visual way of seeing that D equals modulus of z minus w. So it's a bit of a more intuitive explanation as to why the distance from z to w is just the modulus of z minus w. So hopefully that helps help you remember this important fact, because you really do use this idea quite a lot.